Okay, so in this video, we are going to begin to look at area under a curve. And I mentioned in our previous video where we looked at how to evaluate definite integrals, that definite integrals have an application to area under the curve. And in our next video, we'll get to putting that together. But today what we want to look at is different ways that we can approximate the area under a curve. And two common methods are using the left and right point estimates. And what we do when we use the left and right endpoint estimates is we break up the area under the curve into a series of rectangles. And the rectangles, if it's a left endpoint estimate, the rectangles are drawn so that it is their left-hand corner that touches the curve. So the height of the rectangle is defined by the coordinates of the point at the left-hand side of the rectangle, whereas a right endpoint estimate, it is the right-hand corner of the rectangles that will be defined by the function, the y value of the function. So just have a quick think about if we were going to use a left endpoint estimate where we had an increasing function, okay, like what we're seeing here in this top left box, we would see that if we used if the function was going up and we were using the left endpoint to define each of the the heights of each of the rectangles would all end up sitting below the curve. And so therefore, if we were actually trying to calculate if the exact area that we're actually trying to approximate is, you know, that full area there, what we're doing is ending up with an underestimate. Okay, so the left endpoint estimate, if the curve is increasing, will be less than the actual area of the underneath the curve. Whereas if the function is decreasing and we're approximating the area bounded by the curve and those two vertical lines and the x-axis, we're actually ending up with an over-approximation, because if the curve is decreasing but we are using the left endpoint estimate, then all the rectangles are going to protrude above the curve, and so we're ending up with an overestimate. So the left endpoint estimate would be greater than the actual area. And the reverse is true for the right endpoint estimate. If the function is increasing and we use the right endpoint estimate, we can see that the rectangles will protrude over the function, and so we're getting an overestimate for the actual area. So the right endpoint estimate is greater than the actual area. Whereas if the function is decreasing, going down as we go from left to right, our right endpoint estimate will be an underestimate of the actual area, so to be less than the actual area. Okay, so this really just requires you to work with your function and to calculate area of a series of rectangles. So for y equals x squared, we want to calculate the approximate area between the curve, so that's the red line, the x-axis, okay, so that's pretty self-explanatory. So the curve, the x-axis, and the lines x equals 1 and x equals 5. Okay, so x equals 1 is that, x equals 5 is that, that's my curve, y equals x squared, and that's my x-axis. Okay, so it is this area in here that we are attempting to approximate. Okay, and we're going to approximate it using the left endpoint estimate with intervals of width 1. Okay, so we want to now divide this region into intervals each with a width of 1, and each of those intervals we draw a rectangle such that the height of the rectangle is defined by the left-hand corner. Okay, so we're going to get 4 rectangles that we need to calculate the area of here. Okay, so the key thing, let me just get rid of a bit of that notation so we can see clearly again what's happening here. So the key thing is that we're going to need to work out the y coordinates of each of these 4 points, because they define the heights of each of the rectangles. So if I call this y equals f of x, then we can think about that the area, which is, well, not the area, but the left endpoint estimate for the area, we're going to have 4 rectangles. The first rectangle has a width of 1 and a height that is defined by f at 1, the value of the function when x equals 1. Plus, our second rectangle has a width of 1 and it has a height that's defined by f at 2, okay, the value of the function at an x coordinate of 2. The third rectangle has a width of 1 and a height that's defined by f of 3, okay, the value of the function when x equals 3. And the fourth rectangle has a width of 1 and its height is defined by f of 4. Okay, So we need to work that out. Now the other thing to notice is you will always be dealing with problems where you use the width of the rectangles will be the same. So in this case they're all 1. So that's in our expression here, these 4 ones here. Now I know it's 1, so it's a bit trivial in this instance, but let's imagine a more general situation where it could be 2 or half or whatever it might be. So what we can think about here is we can actually just take out the width. So the left endpoint estimate is going to be the width of each rectangle multiplied by the sum of all the heights of the rectangles. Now next year we'll have a look at how we can use something called summation notation to express the sum of the heights quite succinctly, and that actually leads us towards how we use a definite integral. And so you would need that if, for example, we were going to divide this region into, say, 20 rectangles. This would get quite tedious. So thinking about how we can sort of formalize that sum of the heights of the rectangles. But for now, we'll be dealing with quite simple problems, and we'll simply just work them out. So if I've got my CAS available to me, the quickest way for me to do it would be to take the time to define my function, f of x equals x squared, so that I can then literally just type in f of 1 plus f of 2 plus f of 3 plus f of 4. Let's work by hand. Let's imagine it's a tech-free question, and the function's quite easy. So f of 1 is 1 squared, f of 2 is 2 squared, f of 3 is 3 squared, and f of 4 is 4 squared. So that is 1 plus 4 plus 9 plus 16. 1 plus 4 is 13, sorry, 1 plus 4 is 5, plus 9 is 14, plus 16 is 30. So it's 1 times 30, and so it is 30 square units. So this is indeed an area approximation for the area. Now we can see from our diagram that that's an under approximation for the actual area between x equals 1 and x equals 5. The actual area we would expect to be greater than 30. We also want to introduce the trapezoidal estimate, and the trapezoidal estimate is actually just the average of the left endpoint and right endpoint estimates. Okay, and if we think about that, let me deal with an enlarged situation. So let's say you're going to approximate the area from here to here, just using one rectangle. So if we did it using a left endpoint estimate, it would be that area there. If we did it using a right endpoint estimate, it would be that area there, okay? And if we were to average those two, add them together and divide them by 2, okay? So if we imagine kind of adding that purple area on to the green area and then splitting it in 2, it's actually the same as us doing this, splitting that green section in the middle there in half. If you've got the purple up there and the purple down there, then if you take this middle bit and split it in half diagonally, that's going to give you the average of those two things graphically. Okay, so that means that when we are calculating the trapezoidal estimate, which is to essentially not make a rectangle but instead make a trapezium by just directly joining the two points on the curve with a straight line, we get an average of the left endpoint and right endpoint estimates, and hence we get a much better approximation for the actual area. So again, we can think about whether we've got overestimations or underestimations. It's less about it being an increasing or decreasing curve, because if it's just a straight line going up, then the trapezoidal estimate will be perfectly exact. If the curve goes this way, it's still increasing, but the trapezia will sit underneath the curve. Okay, so it'll be an underestimation. But if it curves this way, the trapezia will sit above the curve, so it'll be a slight overestimation. So we need to think about finding the area of a trapezium. Okay, we don't normally see them drawn this way around. We usually see them drawn like this. Okay, A and B, and the height has to be perpendicular to the two parallel sides. However, it's still a trapezium. We don't have to have, two different angled ends. This can be at a right angle, which means that distance there gives the height, and A plus B. And so therefore up this way, that's essentially the height of my trapezium, okay, which is the width of the interval, and then our two heights are A and B, okay. And so this is our formula here, half times A plus B, so times the sum of the two parallel lengths, and then times the height, which in this case will be the width of the rectangle. Okay, so let's use the trapezoidal estimate with 4 intervals of equal width to approximate the area under the curve f of x equals 4x minus x squared between x equals 0 and x equals 4. Okay, so you've been given a lot of information here because they already draw out the graph for you. You're not having to interpret much here. So if we were to think about that quadratic, okay, so common factor of x times 4 minus x, it's clearly a sad parabola with intercepts at 0 and 4, which is what we are seeing here, 0 and 4. So we want to approximate the area between 0 and 4, so we're literally trying to approximate the entire area under this parabola, okay? And we're going to do that by dividing into 4 equal intervals, okay, into intervals of equal width. So that will mean each of them has a width of 1 again, okay? And we're going to use the trapezoidal estimate. Now, the first thing we notice here, and this is where even if the question doesn't provide you with a graph, the first thing you need to do is draw a graph, okay? So what we see here is we've got really nice symmetry, so we actually don't need to find the area of 4 trapezia, we actually only need to find the area of 2, okay? So we can simply split it down the middle and double it because we've got the symmetry, okay? So we want to be looking for symmetry. And also we don't actually need to find the area of 2 trapezia because in this instance, we've got 1 trapezium. So 1 trapezium, I'm going to highlight that in orange here. And then we also have 1 triangle because we get straight down to the x-axis here. So we simply want to think about, oh sorry, that should be orange. We simply want to calculate the area of those 2 shapes to get our trapezoidal estimate, okay? So the trapezoidal estimate is going to be 2 lots of this plus 2 lots of this. Okay, so we already know that that's 1 and that's 1. Let's work out these this point here and this point here. We actually already know the one at the top. Oh no, no we don't. We know it's when x equals 2. So this is 2f of 2. Okay. So if we substitute 2 into the function, we get so f of 2 is 4 times 2, which is 8, minus 2 squared, which is 4. So it's 8 minus 4, which is 4. Okay, and this point here is at 3 f of 3, or it's the same as f of 1. Okay, f of 1 equals f of 3, so f of 3 is equal to f of 1. 1's easier to substitute in. It's 4 minus 1, so that's 3. Okay, so this is the point 3, 3. Okay, so therefore that means that the this height here is 4, and this height here is 3, and so therefore the height of the triangle is also 3. Okay, so we can calculate our areas. So we can have 2 lots of, so trapezium, half times the height, which is 1, times 4 plus 3, which is 7, and then we're going to have plus 2 lots of the triangle, which is half times the base, which is 1, times the height, which is 3. Alright, so in this case our 2's and our halves are going to cancel out, so that's really nice. And then we just have, 1 times 7, so it's 7, plus 1 times 3, which is 3. So it's 10 square units. And that's a pretty close approximation for that area. It's a slight underestimate. The actual area we would expect to be a little bit bigger than 10. Okay, example 3. Let's use 4 rectangles of equal width and the right endpoint estimate to approximate the area under the curve f of x equals 2 to the power of x between x equals 1 and x equals 3. Okay, so therefore this point is going to be 3f at 3, so we need f at 3 for the height of that rectangle. This point is, well that's not 2, sorry, that's 2.5, so that's 5 on 2, f at 5 on 2. This point is 2f at 2. This point is 3 on 2, f at 3 on 2. Sorry, I've got quite a fat pen here. And that's all we need. So 1 is not the height of a rectangle. It's outside of, we're only finding the area between 1 and 3, so we don't need a rectangle past here. Okay, so let's think about what we've got here. So our right endpoint estimate in this case is going to be equal to, now the width of each of those rectangles is a half, So it's going to be half times, and then I'm just going to add up the heights of each of those rectangles. So that is f at 3 on 2 plus f at 2 plus f at 5 on 2 plus f at 3. Okay, so it's going to be half times 2 to the power of 3 on 2 plus 2 to the power of 2 plus 2 to the power of 5 on 2 plus 2 to the power of 3. Now obviously if you've got your CAS this is all very easy, but let's practice a bit of number work here and index laws in particular. Okay, so we can think about this in a couple of ways. What we might think about here is dealing with these two powers of a half. So we can't add, there's no index laws for adding, okay, but we want to actually evaluate each of these things. So if we think about this, we could do this in a couple of ways. We could think about that this is 2 to the power of a half cubed, okay, so I might think about it that way. And then this is, or the other way we could think about this is that this is 2 to the power of 1 plus a half. That might be a better way to do it actually. 2 to the power of 1 plus a half. 2 squared is 4. This is 2 to the power of 2 plus a half. And 2 cubed is 8. Okay, so the advantage of that is when we add powers when we're multiplying. So this is the same as 2 to the power of 1 times 2 to the power of a half. Okay, this is, let's add that 4 and that 8 together, we'll put that as a plus 12 at the end. And then this is the same, this is 2 to the power of 2 times 2 to the power of a half. Alright, so we've got half times, so that's 2. 2 to the power of a half is root 2, that's 2 root 2. This is 4 times root 2 plus 12. Okay, so what we've actually got here is half times, we've got 2 root 2 plus 4 root 2, which is 6 root 2 plus 12, and then let's halve everything, so that is 3 root 2 plus 6. So it is 3 root 2 plus 6 square units. Again, let's check that. If we have our CAS, the quickest way to do this would be to define f of x as being equal to 2 to the power of x. And then we're simply going to work out what is 1 half times, let's just do f of 3 on 2 plus, get that other way, plus f of 2 plus f of 5 on 2 plus f of 3, which gives us 3 times root 2 plus 2, which, yes, if we expand it out, we get our answer, or if we factorise our answer, we get the answer on the CAS. Just to note, if you had typed in half times, so if instead of thinking about these as being 3 on 2 and 5 on 2, if you had instead typed in f of 1.5 plus f at 2, and I know it's quicker to enter that in, so that might be tempting, f at, that's 2.5 plus f at 3. The minute you enter decimals into the calculation, your CAS thinks, oh right, she's happy to work in decimals, or he's happy to work in decimals, I'll give her the answer in decimals. So it'll give me an approximate answer. So if you want an exact answer, you have to use fractions when you type in your expression. Okay, let's do one final example where we're not given the diagram, so we need to sort of think about what's happening here. Use the left endpoint estimate with rectangles of width 1 to approximate the area bounded by the curve f of x equals x squared minus 3x, the x-axis, and the lines x equals 0 and x equals 5. So the first thing we must do is draw the graph. Okay, so this is, if we factorise this is x times x minus 3. So that means it's going to be a happy parabola with x-intercepts at 0 and 3. Okay, so let's draw that. Now, I'm just being a bit careful here about what's happening, because I want to make sure that I can see from x equals 0 to x equals 5. So I want to have x-intercepts there, and I still want to be able to see x equals 5 on the graph. So let's maybe start from there so we can be clear about what's happening. Okay, so that's essentially our graph. Obviously it continues on from there. Now we want to approximate the area that is bounded by that curve, and obviously that curve continues from up there as well. So it's going to be the area that's bounded by that curve, the x-axis, and the lines x equals 0, which is the y-axis, and x equals 5, which is here. So it's the area that's bounded by those lines. So you have to be looking for regions that are fully enclosed. So that is this bit in here and this bit here. Okay, that's what we're approximating the area for. We're going to do that using the left endpoint estimate of with intervals of width 1. So that means we're going to have 1, 2, 3, 4, 5 rectangles. Okay, and each of those rectangles will be the left-hand corner that's defined by the height of the function. So I'm going to start with the second rectangle because the first one's a bit more confusing. So we're going to extend to the function. We're going to hit the left-hand corner, and in fact, because it's symmetric here, it's going to also hit the right-hand corner. Alright, my second rectangle, the left-hand corner, will define the height of the rectangle. Okay, so it's that point that's defining the height of the second rectangle. It's that point that's defining the height of the, technically it's the third. So let's go back to the first rectangle. The left-hand corner, when I work out what f of 0 is, it's actually just 0. So there actually isn't a rectangle there. Okay, so we've got that. Then again, here between 3 and 4, it'll be f at 3 that defines the height of the rectangle, so we won't get a rectangle there. And between 4 and 5, it'll be f at 4 that defines the height of the rectangle. So actually, by the time we sketch it out, we actually only have the area of 3 rectangles to find. And that's because technically what's happening here, if we worked out our left endpoint estimate, it would be 1 times the sum of each of the heights, and the heights would be defined by f of 0 plus f at 1 plus f at 2 plus f at 3 plus f at 4. Okay, but the fact that this equals 0 and this equals 0 is why actually we didn't get a rectangle there and there. Okay, and f at 1 and f at 2 are the same value, which is why these two rectangles are the same height. Okay, so maybe let's work those things out. So we have 1 times, it'll be 0 plus, now f at 1, so it's going to be 1 squared minus 3 times 1, so it's 1 minus 3, which is negative 2, plus, now the other thing is though, and we need to be a little bit careful here again, it's an approximation for the area. So actually, we don't want to use f at 1 here because f at 1 is negative 2 and that won't give us an area. We want to actually use 2. So we do need to be a little bit careful about this. So perhaps in this instance, I'm not going to write out this line. I'm going to think a bit carefully about what's happening here. So this is the point 0, 0. This is the point 1, negative 2. This is the point 2, negative 2. Okay, you can check that. 2 squared is 4 minus 3 times 2, which is 6, so 4 minus 6 is negative 2. That is the point 3, 0, and that is the point 4. Now let's work that out. 4 squared is 16, minus 3 times 4 is 12, 16 minus 12 is 4. Okay, so actually, if we think about, our first rectangle is 1 times 0, our second rectangle is 1 times 2, its height is 2, it's a rectangle. Our third rectangle is also 1 times 2, our fourth rectangle is 1 times 0, and our fifth rectangle is 1 times 4, it has a height of 4. So we've got 0 plus 2 plus 2 plus 0 plus 4, that's our 5 rectangles, and so we have 8 square units. Okay, so we want to complete exercise 21A, the questions listed there.